Welcome to the Computational Economics course. My name is Fedor Ishkakov. In this first video, I will introduce the course and talk about some administrative questions and foundational details. Computational Economics is the course that will teach you basic programming and computational skills in economic analysis. The main idea is that by the end of the study, you will be able to take a numerical approach to some familiar mathematical problems and economic models. We will also pay some attention to graphically representing familiar ideas from economic modeling. And the reason for doing this is not only that it's a good skill, but I strongly believe that understanding of the performance of economic models is greatly assisted by graphical representations of the simulations from these models. As you will see, it's also very useful for example, debugging your code, making sure that the code that you've written is producing the right thing. In the process of working with this numerical economic models, we will also learn some standard and basic computational techniques, such as function approximation, interpolation, numerical integration, and things like that. We will look at the tools that work with the data, that you need to work with the data, and we'll do a little bit of data work as well. So what is computational economics at large? I would say that, under this term, we understand the use of computer in economic modeling or economic analysis. And this is something that is becoming more and more common because the models that economics work with, they tend to be more realistic, and that implies they're more complicated and a lot of the times may not admit an analytical solution. And therefore, we may want to compute the solutions of the economic models such that we understand what they imply. The examples of this numerical work can be found anywhere across the economics field. In macroeconomics, these are various heterogeneous agent models, overlapping generations models. In microeconomics, a lot of I/O is based on computational techniques and numerical solutions, such as topics in dynamic games, for example. Structural econometrics is the field of econometrics where the estimates is based directly on a theoretical model, which usually has to be solved on a computer before it can be taken to the data. And some advanced econometrics techniques may also require heavy use of computer, and here, of course, we touch with machine learning as a field. Although we will not pay much attention to machine learning in this course. So what will you learn? You will learn to code up a given economics model and solve it numerically. So this course is a lot about basic programming skills and teaching you how to better design and write a code. If you had programming experience, that's always a plus. But we will, talk about how to make your code more efficient. You will have to, and you will know how to implement familiar mathematical methods on a computer, and sort of generally how to study the behavior of the economic model. For example, we will analyze what happens with the implications of the model when the fundamental parameters change. We will also learn how to manipulate and visualize the data. So a little bit about myself. My name is Fedor Ishkakov, or Fedor Valentinovich Ishkakov. I'm professor of economics at the Research School of Economics of the Australian National University in Canberra. I've got my PhD in economics from the University of Oslo in 2009. And before that, I became the candidate of science, and before that, I studied at the economic cybernetics department at the St. Petersburg State University. You can reach me on this email given here. If you have any questions, never hesitate to write me and ask. I keep the research interest. So I mainly do applied econometrics projects with structural estimation of dynamic models and some methodological things around it. And applications span several fields from labor, structural labor to IO. Okay. And there is a link to my website. You can find any additional information or whatever information you may need over here. Okay, so normally I would ask students to introduce themselves as well, but since we're doing this synchronously, it will be your first task on the weekly assignments, or it will be part of your first task. Right, so the schedule, this course will be delivered remotely and asynchronously primarily, and that means you will be watching videos and performing assignments, and I will be giving feedback and grades. But there will be bi-weekly, fortnightly synchronous sessions as well. And so we will meet in Zoom. This will be sort of like consultations or tutorials which are driven by you. There will be question and answers. I will aim at publishing the teaching materials on either Tuesday or Wednesday each week. And then these question and answer sessions we will run from week 3 and do it every other week. Well, if there is need, we may have more. And again, if you have additional questions or anything, just don't hesitate to write me an email. So what are these lectures and tutorials? The materials in the course is organized along topics, and you will have a list of the topics that I plan to cover. And the technical topics, especially in the beginning of the course, we will be sort of learning how to write code, and more of economics will come later. But even in the beginning, I will use economic examples for everything that we do, or mostly economic examples. Now, the videos will be of two types. A theoretical video is like a lecture, where I'm sharing concepts and showing maybe some little examples of this and that. And then there will be practical videos, which are basically sharing the hands-on experience. So you will be able to see how I code, and I will sort of talk through the process of writing a code and coding up an economic problem. The resources here are 3. The first one is a book, which is actually downloadable. It's a PDF file, which is linked here. Now, CompEcon is a wonderful resource that you really need to know about. It has tons of lectures and actually notebooks, as we will be using. For programming basic and more advanced topics, primarily in macroeconomics. The Dynamic Economic Quantitative Methods and Applications by Russell and Cooper has a wonderful sort of background for the things that we will do in the second half of the course. And there will be additional materials for you to look at in the end of each video or notebook. All right, now let's talk about assessments. First part of the assessments are the problem sets. They will be distributed weekly, and I will grade them maybe within 7 to 10 days, or at least that's the plan. And they in total, all of the assessments will constitute 25% of the final grade. The midterm assignment will be like a larger weekly assignment with several steps to complete, working on a particular economic model or problem. This will come in the middle of the course, and so will be based on the knowledge that you get in the first half of the course. Now, 27.5% will be the weight of the grade for coding and implementation of the economic model, And on top of that, 20% of the grade will be about video presentations. So you're supposed to not only complete the assignments in the notebook and write the code, but also talk about your work in a similar way as you see now. Although, of course, the video setup is not important at all. So just a screencast with your explanations of the logic of why you did this or that will be sufficient. Finally, there will be an exam in the end of the course. This is going to be an open book exam. Any resources are allowed. The only constraint is that you will only have 3 hours to complete all of the questions. The questions will be various. There will be short questions for knowing the facts that you should not spend any time on. There will be several mid-sized questions to search for a bug, for example. So some time will be spent there. And there will be several small but sizable individual coding tasks. So these will take most of your time. And, as always with open book exams, the trick is to manage your time correctly. There will be not enough time if you don't sort of pace yourself. The final exam will be 27.5% of the final grade as well. Now, in terms of communication with me, I will make announcements on the course page. You will get the link. Now, you can always email me, as I was saying, so please be completely free to use my email and ask me any questions. We will do Zoom by appointment if you really need to talk to me. All right, now a little bit about the way this course will be taught. We will use version control, software Git, and we will use the online community for coders, GitHub. I presume that many of you already have experience with these systems, but for those of you who don't, I can say that this is an essential part of any efficient coding work and definitely in computational economics. So knowing Git version control is part of the course. You are supposed to learn it in this course and be able to use it. And, communicating through repositories and commits and things like that will be our primary way of sending around the code, assignments, final exam as well. So this is very important. Now, I cannot force you to be part of the GitHub and register there. I think it is quite standard, and I don't have a good reason why you wouldn't register on GitHub and use the machinery that it provides, which is an efficient way to work together with somebody and to work in a course, with me. But if you don't want to do that, we'll find alternative ways. Just write me an email. Now, I will be using Jupyter Notebooks. We are looking at Jupyter Notebook right now. This is, in slides mode, but it's actually a collection of cells, as you can see here. And you can put text and LaTeX, there is no math, pictures, whatever, into these cells, but also code. And so this will be quite useful. It is a very nice tool for presenting your sort of prototyping work or simple code. It's not very good for sort of big software projects, but for teaching, I think that's quite ideal. So we will do all of the assignments and exam in the notebook. And every time you present your work, I think you should think of notebooks as a useful tool. The course is in Python. We could do different languages, and I myself use different languages for different things. But I think, Python as a general purpose language will be most useful for you no matter if you stay in academia, continue with your studies, or go do some work for the industry. I think knowing Python is a really important and valuable skill that can be shared outside of your studies, can be useful. Of course, it's a free open source language, so we can all work in the same environment, which unfortunately is not the case for other scientific computational packages like, MATLAB, for example. And even though it's an old language, it's been used more and more, and it's been adopted very widely in the last decades. And new libraries are being produced, which makes Python even more suitable for scientific computation. So here's a somewhat old now graph. You can see that the projections start from somewhere around here. But this is popularity of Python. This is measured by the overall questions views each month, and the data comes from Stack Overflow. You can see that the Python community is really growing, and this is one of the reasons what makes Python such an attractive language for you as well, because there is a lot of synergy around it in the later years, and that will make you more efficient too. Now, Python has a huge array of applications. The language is easily extendable, and the modules and libraries which are written by other people, they cover lots of different fields and topics of everyday life. Of course, we are mainly interested in scientific computing, and we will look at the packages and libraries that are needed for scientific computing. But, if you're doing web development or desktop applications or, business analytics or even games, or you work with the data, all of this can be done with Python with appropriate libraries and modules. And did I mention that machine learning can be done in Python quite efficiently as well? So, data analytics is, generally data science can be done in Python quite well. Now, a little bit of a background and a discussion of why I think Python is a good choice. The thing that you really need to know about sort of programming in general is that there are two levels of programming languages, low-level languages and high-level languages. Where low means that you're much closer, you're lower to the motherboard of your computer, and so you have a much more direct access and control over the computer resources. That makes languages like Fortran, C or C++ really fast compared to the high-level language, but also very verbose, which means that you have to write a lot. You have to type a lot to achieve the same task as you would in the high-level language. High-level are usually slower, although it depends on the circumstances and tasks. For example, MATLAB is very slow in loops, but it's pretty good for matrix algebra and matrix manipulation. The thing is that you don't need to write as much code, okay? And usually with additional libraries and packages, it's really versatile. So, how do we choose? Well, here's the trade-off. These dots don't really mean anything, therefore there are no tick marks on the axis. Well, they do mean they convey the picture of the trade-off between productivity and machine speed, right? So languages sort of tend to locate along this diagonal. With some languages or all languages trying to get that way. And so as you can see, Python is generally or used to be very slow, but productivity in terms of writing the code is high. But with additional libraries like NumPy and Namba, Python is moving into the direction of higher machine speed as well. Here's a comparison of how much code you have to write in different languages. Here, for example, this compares Mathematica and argues that Mathematica is a really concise language which will not take much time to develop a program in. It's writing mathematical formulas which can be directly interpreted by a computer. So to do the same thing in C that you would do in Mathematica, you need to write 8 times more code. That's how you read these numbers. And so MATLAB, is 4 times less writing code than C. And so thinking about Python requires more code than Mathematica and more code than MATLAB, but not much more, less than 2 times more. And yet Python gives you a lot more control and a lot more versatility. You can do a lot more different things with the language. But, this is something to be aware of. In terms of comparing speed, I'm thinking of economic applications, first of all. There has been several papers, and, not only in economics, this is a more general comparison here. But what do we have? So here, Fernandez Villaverde and co-authors compare different languages in solving a fairly standard macro model, if I remember correctly, representative agent model. And you can see that if C++ is normalized to 1, then languages like MATLAB take 26% more longer. R is a lot slower, but Python is sort of doing all right. It's slower, yes, but not much slower. Here's a comparison, different compilers as well. Now, how should we take these numbers? I would say these are really indicators of the comparison of the machine speed. And what's really important to keep in mind is that the real objective function is the development and maintenance time, where maintenance is also very important, plus the runtime, and you have to take into account how many times you want to run this code. And that's the sum which should be minimized. And of course, learning and investing a lot of time in code development into a language which has really low runtime, so that code runs really fast, makes sense if you have to run it many times. And that's what you have to do in structural econometric applications, for example, but not in macro, or not as much in macro economics. And therefore, developing and maintenance time is really important component here, and this is what you really have to keep in mind all the time. In terms of trying to make the higher level language faster, we always have to think about vectorization and parallelization, or scalability of the computations. And we will talk a lot about vectorization in this course and somewhat less about the parallelization. Okay, so to sum up, why do we use Python in economics? Well, it's a versatile, high-level programming language that does not require too much time or too much code to achieve a particular computational task. It has very good scientific libraries, and the libraries that we will be working with all the time is NumPy, SumPy, SciPy, Pandas, and Matplotlib. It allows for parallelization and just-in-time compilation. So this will touch a little bit in the course, but the idea here is that even Python code can be translated into the machine language or machine codes and be as fast as the low-level languages for some particular tasks. Machine learning is possible in Python, so even though we will not do this in this course, it's important to know that you can use TensorFlow or Scikit learn packages to do artificial intelligence applications. Very vast field of different other libraries. And then, of course, there's a really nice community, for example, on Stack Overflow, that can provide answers to the standard problems that you may have some questions for. Okay, so this concludes this introductory video. Here is an example of further learning resources, which I will make sure to provide in the end of each of these little segments. And so here you can see a couple of examples of the discussion of how to choose programming languages. CompEcon here lays out some arguments for Python, and Florian Oswald from Science is Poor, he's coding in Julia, and you can find some arguments of his here as well. And here's some more on comparing the languages. Okay, thank you. I'll see you in the next video.